So I'll wrap her up here. I've had some similar experiences that some of the past speakers talked about, where the IQ and all. So there's some funny overlap when you put your presentation in a bubble together, and then you see how other people view that person, and you see all this shared synergy. It's pretty fun. It's been entertaining seeing all that. So I've enjoyed it. So my title is kind of a loving title. This was a term actually coined in part by Bruce. When we started working together on some research projects, we would discuss how to do research. How do you design a good experiment? What's going to be valuable to the industry? And a term came out of our conversations that we basically said this is kind of low-tech research, which most professors would run from low-tech research because it doesn't put them on the map in their mind. It doesn't let them hire a bunch of graduate students to present at ACI in their mind. But actually, I spent a career doing low-tech research, and I couldn't be happier with the body of work that I was able to produce with both undergraduates, which is very hard to do, and with industry icons. All the good ideas came from them. It came from sitting in committee meetings and coming out of those frustrated about the lack of just good, hardy data to support some of the positions that we have today, and basically to move the industry forward. So was very excited when Bruce and Ward started approaching me for help, and I just love that they were willing to take the time and invest in undergraduate students. So in addition to honoring Bruce today, I'm really sending a message to industry and academics. I don't know if there's any academics in the room, but this is a very important relationship. We always talk about making sure industry and academics are connected, but there's a lot of layers to that. I mean, hiring them and coming and doing guest speaker spots are all really important, but this is a layer that most students don't get to experience because they don't go to grad school. And to have the love of research, I think, is a really cool jumping off place for ACI. To get young people engaged in ACI or ASCC or InterMCA or TRB, research is kind of that intersection. And to allow undergraduates to experience and taste that is really, really important. And along the way, we can get some really cool data out of that experience as well. So I did a little similar kind of Google searching as the other speakers, because I was thinking about the impact that he had on me and the impact that he had on the students that I taught. So I taught at MTSU for 20 years. Well, Bruce taught for 15, 16 years as well. And I took a lot of inspiration from that because he crossed over into industry and he had so much empathy for a college professor. So when we would sit and talk, he understood my constraints, and he understood how important it was to give back in a little different way than maybe you pour into graduate students, for example. So just those 16 years, just round numbers, knowing the impact that he had, 2,400 students, give or take, likely benefited from the impact of Bruce. And I think that's, I'm very proud of the 1,500 that I was able to impact in my years. So knowing that there's that many students that are out there with a healthy career behind them or in the middle of is exciting. I was able to spread that love in so many different places. I also was curious at what his PhD dissertation was. So I Google searched that, and at Montana, he did a dissertation on curvature ductility of concrete columns. And I thought, wonder how did that survive? What's today's conversation on curvature ductility? And it's alive and well. You can Google curvature ductility, and a ton of YouTube videos pops up of people trying to explain curvature ductility. So it's very common in an engineering curriculum. It's something that a lot of people have to pay attention to. You can see the kind of math associated with it. So Bruce, your research is alive and well, and you can't always say that about PhD dissertations. So that's pretty cool. I kind of to similar Google searches that other people did, particularly Scott, where he Googled what all those papers, right? So just a few things, right? I Googled concrete construction, where you did the 4 construction pros. 84 times Bruce's name's on there. I did an abstract hit on ACI, 62 abstracts had his name on it. I know there's countless ASCC impact, but the one that maybe we don't have a number to, and I would love if Bruce commented on this, is how many negative votes he cast at ACI with very well-constructed comments. I can imagine I couldn't find it, of course, anywhere, but I can only imagine how much that number is and how important those dozens potentially of ACI negative votes are. That's why we're here, right? We're, kind of back to the devil's advocate. Playing devil's advocate sometimes is one of the best roles you can play in a room. So the CIM research impact that he had, so I taught in a program that was focused on the concrete industry, so I was fortunate in that I already had the love and the passion for concrete. Engineering curriculum all involves concrete as well, but it's in a smaller segment, so my whole goal was to educate and train concrete professionals. So it was an easy relationship to talk to industry icons like Bruce, but I went back and I counted up the number of semesters that Bruce worked on projects with me, and some of those projects carried over into multiple semesters. Sometimes they were one semester projects, but about 10 different semesters. We worked with about 20 different students in each semester. So just in that little window, he took the time to mentor through me and with them personally. He visited either at the campus or at an ASCC event. We would get around a table and talk. He not only allowed MTSU students to benefit from this, we had other concrete schools that benefited on a particular project. So again, that impact, even as an industry professional, he cared about students, he cared about moving the needle forward on data and progress, but he utilized, I think, a unique vehicle to get it done. So this is where some of the overlap happens, but I love it. I felt like the formula to get all these good ideas out of Bruce was to make sure he was wearing a Hawaiian shirt, make sure we were sitting around a table with margaritas and students, and just talk shop. Just talk about what were the pains that he was having coming out of committees, what were the hot topics. Somebody mentioned hot topics. That's really what my conversations with Bruce was what's hot right now, how can I stay relevant as a faculty member. That's really important to faculty, staying relevant, having a body of work that means something here at ACI or other forums. So I was really appreciative that he was keeping me in the loop, essentially. And I just was always hungry for what's next and what are you working on and what's important. So that was important. The other piece of this formula was the dynamic duo, of course, of Suprenant and Ward Malisch. I was so appreciative that those two collectively took the time with me. I think it's interesting when I think about the two of them, they both started their career in academia and then migrated over into industry. And unbeknownst, I'm doing the same thing. I've left academia and I'm now crossed over the fence and jumped over into industry, and it's been a great decision. I think what I learned from my PhD professor was the quality of research doesn't have to be 2 and 3 and 4 year data sets. You can get a very meaningful data set in a few months with a few hard backs. Basically, we used the backs of undergraduate students to just get a body of work that meant something to an industry forum. So this dynamic duo could take lots of shapes. I tried to think of one image that could capture Bruce and Ward, which is very difficult. So I just found a couple of different images that I just felt like it was all, they have all these personalities. They are the Batman and Robin, right? They are these duos. It's so interesting, their relationship and how they turn that relationship outward. They're so willing to share that relationship with others, which is so important. I definitely felt like I got all versions of these folks, of these duos. But what my favorite picture is when I would open a CI and I saw these two faces at the end of the article, I was excited. I was excited to read the paper. I knew it was going to be something good. Even if it was just one of their faces, that was the first article I was going to read in CI. So these two gentlemen, again, poured into me and poured into our students in a way that I think is unique and definitely appreciate that. So real quick to the academics in the room, if there are any, or even to the industry folks that might want to make a relationship like this, the idea is really finding a mechanism in the curriculum that allows for this kind of free thinking. I think our students don't get enough opportunity to free think, to critically think, right? And to take something that you don't really know what the answer is going to be. You don't have an answer. You're trying to seek an answer, and you're trying to understand that not all answers at the end are going to be what you want to hear. Somebody mentioned that earlier. Sometimes you get a data set and you're like, well, that didn't help me on anything. But now I know I'm smarter. I know something, a different direction I need to go. And undergraduates need that desperately. probably more today than ever. So to have the opportunity to connect in curriculums have decreased. They've gone from I think I had 138 hours in engineering. All curriculum now is about 120 hours. So there's less time to get really important things done. But fortunately, there's still opportunities like independent studies and special problems classes. Capstone could be an option. We built a course called Senior Concrete Research, which is the best course that I ever taught, because every semester I would put out a call to action to all of my industry partners, and I would say, what ideas do you have? What data sets do you need? And I had a built-in data set every time I needed it when I would talk to Bruce, but I would reach out to lots of companies, admixture companies, cement companies, anybody, producers. What are you working on? Is there anything we can help with? And that sounds easy, but that person that raises their hand and says, I got something for you, they got to stick with that project. So it's not just a throw the idea out and hope for the best. You're working with undergraduates. You got to really put your arms around this kind of concept. So not only does the faculty member need to be pretty dedicated, the industry representative needs to be very dedicated, because you're coming in and really answering what might seem like very fundamental, basic questions to you as an industry icon, but necessary content, necessary conversation for a very youthful 18, 19, 20-year-old that doesn't really understand how to execute a good design of experiment. So there's some work there. There's some definite upfront work. We spent a lot of time exchanging emails and phone calls about designing a good experiment. So that industry mentor piece is really important, but I think it's just a different, unique twist on how to execute research. And then sometimes our data sets couldn't be combined in one semester. My goal was to keep it within one semester on occasion, because I didn't want to change operators. That's one of the kiss of deaths of good research, is changing operators in the middle of a study. So I would try to figure out with the person that was wanting the research done, how can we maybe break this up into ways that I'm not going to affect the end result by having a change of operator, get more out of the work, and let's keep this going if the data is providing a lot of value. And occasionally we had to do that, because typically I needed to get something done within 10 to 14 weeks in a regular semester. And by the time you get things going and you're looking at 28 and 56 day results on some things, you're running out of time pretty quickly. So it is possible to break it up, and the pro there is you're taking a data set that might be small in nature for one semester and really grow and provide more value back to the industry. You've got multiple hands touching, which is a pro and a con, because you now have to figure out, how do I introduce new hands without affecting my precision. So the driving force behind a lot of the ideas that Bruce and Ward brought to the table was really about tolerances, and that's been brought up today. Tolerances have been set sometimes without the consideration for the builder's ability to meet them, or the effect that an out of tolerance condition might have. So that seemed to be the theme of all of our discussions. That also translated over into some specification tracks that are out there, and I think that's where position statements obviously come in and try to rescue contractors and help them. A lot of these statements that you see here, these bullet points, are a direct cause for writing a position statement. Risk transfer, that's a big one in our industry. Specification requirements that are vaguely described, or aren't realistic. Irrational construction requirements. All those are things that, again, make people frustrated and want to pull their hair out, and when you don't have a big enough voice to make a change, you've got to go get data to kind of back up what you're saying. So I'm going to do a quick example of one project that we worked on. This is actually one of the first ones that they brought to the table, and this was as a result of a code discrepancy. So the life safety code kind of entered into this project, and it specifically entered in with stairs. So we did a project where we were trying to determine if the tolerances that were listed in the code were actually being achieved in the field, because there really was not data out there that actually had a methodology for measuring the differences of stair risers to determine if they were intolerant. It was just sort of a tolerance that was thrown out there, and there just wasn't a lot of people measuring it. And I think what Bruce and Ward and myself were wondering is, are any of the stairs meeting it? This also was a result of a lawsuit that was pending or coming. It was something that had happened on a slip and fall, where, again, the tolerances of this particular staircase was being brought into question. And so this kind of created the need to look at the existing staircases and seeing if really we're building to this tolerance today. So the discrepancy was that the life safety code had an extra tolerance listed. The first tolerance is that no adjacent riser shall be different by more than 3/16 of an inch. The additional tolerance was that the largest and smallest riser shall not exceed 3/8 of an inch in any flight. So you take all your stairs and none of them can differ, even if they're not adjacent, by more than 3/8 inch. But if you go look at the IBC and the ACI, they just had the 3/16 tolerance, but they did not have a requirement for the maximum and minimum. So that was kind of brought into question. So you can kind of look at an example there. If you've got stairs that do meet the 3/16, it's very easy to not meet the 3/8 over the course of the staircase. So that kind of began the research. The real problem, as I mentioned, is that if you have a trip and fall accident, much later into the service life of the staircase, was it ever in tolerance? Did it become out of tolerance just due to durability, wear and tear? Who knows? There wasn't a data set that kind of helped support any position, and ultimately that builder could become part of the lawsuit because of that. And we really were curious about cast in place, precast, or concrete pan stairs. So those were also brought into light as was one better than the other, needing and reaching that tolerance. So the research need was essentially that. We wanted to see if that 3/16 was achievable, if 3/8 was achievable for the overall max and min. And we also were kind of curious about whether or not there was any accident history of something that was out of tolerance. And so we were just kind of wondering is a 1/4 inch too much? Is 3/16 really the right number for those risers? And then Bruce did, with his wonderful way of finding lots of reports, he did find a report in 1992 that tried to address this particular gap in the data. So they did an in-depth review, but at the end failed to establish a consistent, valid link between stair safety and stair geometry. So nobody still, by the time we did this work in the middle, I think it was like 2013, we still didn't have a good, clear answer or clear direction on stair construction. So we wanted to have our main goal was to have a good measuring methodology. If somebody was called into question about their tolerances, how do you measure them? There was not a good measurement tool out there, and so we were trying to establish a consistent measuring tool. And we wanted to answer a few questions, as I mentioned before, the 3/8, the 3/16, what was that telling us? Is there, is the top or bottom step more likely to be out of tolerance than other steps, kind of thing. So we were just kind of looking at a lot of different conditions. We did do a lot of this work at MTSU campus. There was a lot of concrete stairs, fortunately, to review. We went into downtown Nashville, found lots of other stairs. Contractors let us in on projects. So we tried to make it very variable. These are stairs leading into our football stadium at MTSU. So we tried a lot of different types. We did 10 sets of stair measurements in 3 different types of buildings. We tried to follow an existing measurement protocol, but the life safety code did not have one. So we tried to create something off of current handrail requirements. And so we did our study with the handrail requirement of 18 inches off of handrail is where you basically walk. So we figured 18 inches off handrail, that's where the wear pattern is going to be. Let's start there. Here was another staircase in MTSU, give you an idea of kind of the body of work there. And the important part of this is just having lots of operators. And so I'll kind of go back to my original motivation. What's great about undergraduates is you get a lot of them. So if you really need a big body of data, you can get it with undergraduates. It's harder to do with a single graduate student or even a pair. But when you've got a class of 20, you can have a lot done. So we were able to spread the load here and do a lot of different testing. A lot of repetitive testing, which is pretty normal in getting quick body of work data. But the idea is just making sure that you're finding some way to make the data reproducible and repeatable. We kind of laid out a precision statement for the work and worked with just very basic tools, carpenter's level. We did set up a survey instrument to line out the 18 inches off the handrail to make sure that was consistent. So we did utilize that, but otherwise it was really basic stuff, which is where that loving term of low tech comes into place. Quick snapshot of the data. So you've got a particular staircase had 13 risers. You took, about 7, 8 students, and you let them, execute the work. So all of this, and we did this lots of times, but a lot of this allowed for really good statistical measuring and results. We were looking at E691 to build our precision statement. So we tried to hit some of the minimums so that we made sure we had enough data to really evaluate for the project and for the study. And then we started building our precision statement for both repeatability and reproducibility. And you can kind of see what ended up coming out of some of these are just 2 of the staircases, but what this allowed us to do is to understand what one operator or multi-operators could do in measuring this methodology, or using this methodology that we were trying to build and create. So what we figured out was that for repeatability, we were able to achieve an average of 7/16 of an inch variability between the same operator, and then an inch of variability between multiple operators. So just trying to establish some baseline. What's possible with the work? What are we going to get out of this? And then what was our data set going to tell us? And really the result was that 30% of the staircases that we checked were out of tolerance. They did not meet the 316, which is both in 117, IBC, and life safety, with a 3/16 tolerance. So 30% of the staircases don't even meet it. Did they meet it when they were constructed? Who knows? But if a slip and fall happened, they'd be held to these numbers. So establishing a methodology that can be employed early in the project, which is what I recommend at the bottom, is having a pre-construction meeting to discuss, if we need to measure this for tolerance, where are we going to do this, which is partly the methodology that we built, and when. Similar to like floor flatness. When do you test it? When is the right time to actually check for stair tolerance? And then what that told us, 82%, that other extra code requirement that life safety had, 82% of the staircases failed that 3/8 from max to min. So again, things weren't even being built to code that had been in place for a long time, just hadn't been challenged, hadn't been looked at in the way that we did. So this indicates a very high percentage of the stairs measured were not within tolerances in a couple of the different editions of the life safety code. So good example of just how you can take some data and move this back into conversation. That data was able to be used in the lawsuit, so it helped, hopefully. I think actually it didn't ultimately end up helping. So I think it's those sort of milestones that really make some of this work feel very special, and I very much appreciate the opportunity to work with Bruce for so many years. And with that, I'll say thank you.